would like to present here the report on the supramolecular self-assembly of ionic polymers with such interesting microcycle molecules as calix for resorcinols. The creation of supramolecular amplifiers is a relatively recent but rapidly developing area of the supramolecular chemistry and colloid supramolecular and colloid chemistry. It's well known from the supramolecular chemistry the microcycle molecules can bind other molecules due to non-covalent interaction. Can bind other molecules due to non-covalent interaction into such supramolecular system as host gas complexes, which, like conventional amplifiers, can be self-assembled in colloids. That's amphiphilic molecules are able to interact not only with each other with formation of aggregates, but also participate in intermolecular interaction in other type of molecules, which leads to formation of supramolecular amplifiers, or supraamplifiers for short. Interestingly, these supraamplifiers are formed by simple mixing of molecular building blocks as a result of non-covalent interaction between them, and then spontaneously assembled to the well-defined aggregates of different composition, type, and purpose than those formed from pure long-chain molecules. Supraamplifiers are attractive because they self-assemble it possible to create functional nanoparticles. Due to the fact the functional groups of one single molecules can be non-covalently attached, such supramolecular design bypasses laborious synthesis and energy costs. The binding blocks for supraamplifiers can be various flexible open-chain and rigid microcyclic molecules between which these supramolecular interactions are realized. For example, addition of non-amphiphilic cyclodextrin to chitosanes led to formation of supraamplifiers in which the hydrophilic and hydrophobic part are linked due to non-covalent interaction, and they form supraamplifiers spontaneously assemble into spherical nanoparticles. The dynamic and reversible nature of this interaction can make the entire supramolecular system sensitive to external stimuli, which creates a potential application of such supramolecular assemblies as a small-scale basis of functional smart nanomaterials. Among the various three-dimensional microcycles, calixarin are particularly interesting. Calixarin based on 1,3-dihydroxybenzene are known as calix for resorcinols, have an additional rigidity in their structure due to formation of methylene bridge between resorcinol oxygen atoms of neighboring aromatic units. They allow toxicity by compatibility and the ability to complex with a wide range of organic and inorganic substances lay solid foundation for their possible biomedical application. Calixarin have a hydrophobic cavity with adjustable size and conformation, and the upper and lower rim of calixarin can be functionalized with a variety of substitutes, conferring various beneficial properties such as binding selectivity, stimulus sensitivity, etc. As such substitutes for functionalization of the microcycle platform, we choose viologen groups, which represents the sort of coordinates for 4-bipyridinium. The modification of calixorine platform by 4 viologen groups ensured good aqueous solubility of the aromatic framework with 4 rather long-tail alkyl chains. Accordingly, thanks to viologen groups, the dissolution of these microcycles in water was achieved, which is very important for creation of biocompatible nanostructures. Before creating superamphiphals based on viologen calixorine and polymers, we investigated the biological properties of the series of emphasized microcycles that differs in the length of alkyl chains on the lower rim. The study of hemolytic activity showed different trends in its change depending on this length. The degree of hemolysis increased from pencyl to octyl derivatives and then decreased with increasing length of alkyl fragments. And the dodecyl microcycle doesn't cause hemolysis of erythrocytes in the studied concentration range. Due to the fact that dodecyl microcycle shows the least chemotoxicity, this calixorine was used to create superamphiphals with polymers. So far, only Kazan has been used in creation of superamphiphals with microcycles. But since Kazan is a cationic polymer and the microcycle started by us carries positively charged viologen groups, different anionic polymers were used as other components of the superamphiphals. We investigated a different set of mixed systems of cationic calixorine with sodium salts of Kazan, carboxymethylcellulose, RNA, and alginic acid. The features of aggregation of these 4 mixtures are identical in that the driving force of intermolecular interaction is the electrostatic attraction of oppositely charged fragments. In order not to take much time, let me give you some more details about mixed composition with the RNA. The study of interaction of biopolymer with microcycles was carried out using to-be-dimetic titration, during which the interaction between them was accompanied by pronounced deviation from the concentration dependence of light transmission and 3-calixorine. Obviously, such deviation is related with opalescence caused by the formation of joint aggregates at a certain ratio between microcycle and biopolymer. The obtained data of to-be-dimetic titration are in a good agreement with the result of electrophoretic light scattering. Zeta potential values were also measured for bus mixed system with the constant concentration of one component and variable proportional of the other. In both cases, the recharge of the positive charge of calixorine and the negative charge of RNA occur after reaching ratios at which there is area of the maximum opalescence presented on the previous slide. The revealed change in zeta potential indicates the electrostatic nature of the intermolecular interaction of viologen calixorine with sodium RNA. Accordingly, the observed opalescence upon mixing of microcycle and polymer is related with formation of joint aggregates as a result of the decrease in proportion of ionic form of both components. Morphological change in RNA and the action of microcycle can be traced using cellular dichroism. The spectrum containing a negative band at 209 and 239 nanometers, as well as the positive maximum at 268 nanometers, indicates that the NEA in pure solution is in a conformation, decrease the intensity and slight red shift of the band at 268 nanometers in a mix with the calixarine probably indicates a conformational change from A form to the B conformation. As the mass ratio, ellipticity almost disappear due to formation of pure soluble complex and further increase in proportion of microcycle in a mixture with constant NEA concentration led to reverse increase in the dichroic absorption of the positive and negative band. The revealed change in ellipticity can be related with the compaction of NEA helix due to electrostatic interaction between positively charged calixarine molecules and negatively charged NEA fragments. And the mass spectroscopy was used to identify the chemical groups involved in intermolecular interaction between microcycle and NEA in water. When comparing a mass spectrum of mixed with that of pure calixarine, a decrease in the signal intensity is observed as a result of the co-aggregation, and the largest chemical shift is experienced by viologen protons distant from positively charged nitrogen atoms, which may be due to a change in the environment of viologen ions as a result of electrostatic interaction with NEA. The upfield shift of protons of the terminal methyl groups and proton broadening of the dodecyl chain in the presence of NEA indicates the participation of microcycle alkyl chains in interaction with NEA, leading to joint aggregation. The formation of joint aggregates based on calixarine and NEA was confirmed by transmission electron microscopy. The image for the pure NEA show fragments of biopolymer. These filaments may be non-polar, therefore general aggregates in water, forming bundles that can be attracted to each other due to hydrophobic effect. The presence of equimast amount of microcycles in water in mixed with NEA leads to the formation of more monodispersed spherical aggregate. So the comparison of image of pure NEA, pure microcycle, and its mixture confirms the formation of joint nanoparticles due to structural ordering action of the calixarine. After verifying that the NEA and microcycle are combined up into single uniformly mixed nanoparticles, we decided to identify their functionality. The first thing we decided to identify was the ability to encapsulate the hydrophobic flavonoid quercetin. Free NEA exhibits a low stabilizing capacity for this flavonoid. The presence of viologen calixarine together with NEA increases the aqueous solubility of quercetin. However, it should be known the encapsulated ability of the mixed system is similar to that of free calixarine. So the capture of quercetin into nanoparticles occurs due to its solubilization in hydrophobic domain of microcycles. When comparing the NMR spectra of the mixed in the absence and the presence of quercetin, the largest chemical shift is observed for the proton of alkyl chains, underscoring the location of quercetin in the hydrophobic domains formed by these chains. After checking that the lipophilic quercetin is solubilized, it was further decided to try to use nanoparticles to bind long-chain oleic acid. Absorption at the 260 nanometers was used to study the interaction of oleic systems with mixed system. An interesting effect of oleic acid on this absorption is found by varying the ratio of calixarin to NEA. In the mixed solution with aqueous ratio, the presence of oleic acid causes significant hypochromic effect until its concentration correlates the molar concentration of calixarin, which suggests that microcycled fragments of adjoint nanoparticles, as in the case of quercetin, is the binding site of oleic acid. Such spectral change were not observed in the UV spectra of the pure calixarin, pure NEA, and as well as the mixture with 10 and 2 excess of NEA. The probable reason for the different binding ability of oleic acid by mixture is the value of the fraction of microcycles, which determines the potential of mixed nanoparticles and the number of hydrophobic domains in the composition of these nanoparticles. After certain that the nanoparticles are able to bind hydrophobic molecules, it was further decided to test the ability of these nanoparticles to interact with hydrophilic doxorubicin hydrochloride. Since calixarin and doxorubicin are similar charged, they will compete with each other for complex formation with NEA. To determine the composition of the mixed system suitable for drug binding, fluorometric titration of the mixture of NEA with drug by microcycle was carried out. Addition of the first portion of microcycles until tenfold excess of NEA doesn't lead to increase intensity of doxorubicin fluorescence, but increase in the emission is observed at a higher concentration of calixarin near the aqueous ratio due to its doxorubicin release from the complex with NEA. A further increase in the microcycle concentration doesn't lead to the change in the fluorescent intensity, which confirms the achievement of the complete release of doxorubicin. Thus, optimal delivery systems for doxorubicin is the composition with a 10-fold excess of NEA, and which NEA is capable of simultaneously binding doxorubicin and microcycle. Fluorometric study of release of doxorubicin in phosphate and acetate buffers was performed using dialysis for this composition, and accelerated release of doxorubicin in the acidic environment is due to protonation of nitrogenous bases of NEA, electrostatic interaction of which with negatively charged phosphate backbones can increase the stability of the ternary structure of NEA. The study of biological properties includes the determination of cytotoxicity effect of the composition against normal, chunk liver, and tumor HeLa cells. Pure NEA and its mixed with calixarin show no cytotoxic effect regardless the amount of the ratio. Binding of quercetin and lactic acid didn't lead to the change in the cytotoxicity against mast cell lines. Free doxorubicin exhibit greater cytotoxicity against tumor cells than normal cells, but when we combine with NEA alone, its anti-tumor activity is almost halved. The binding of doxorubicin by mixture enhances the cytotoxic effect. However, the presence of quercetin had antagonistic effect on the doxorubicin in tumor cells, while the presence of lactic acid, on the contrary, increases cytotoxic effect against HeLa cells. I have got to say that while cell assembly behavior of calixarin with 4 polymers was almost identical, the biological properties of this mixture differed. Encapsulation of doxorubicin in nanoparticles using sodium sulfur carboxymethyl cellulose and alginic acid improves the drug's selectivity. The intracellular content of doxorubicin that entered tumor HeLa cells, both in the free form and in the various formulation, in the absence and presence of antioxidants, was further studied. The fact of the less intense of fluorescence of the free dox compared to its formulation attracts attention despite the same amount of drugs in each sample. Since according to fluorometric fluorescence of doxorubicin, the presence of both pure NEA and mixed with calixarin is lower compared to free dox. The probable cause in the increased intensity detected using flow cytometry is increased affinity of a number of proteins contained in the cytoplasm of HeLa cells to NEA. In addition, fluorescent microscopy reveals the presence of apoptotic cell and the action of the free composition NEA with dox, NEA dox in the mixture of NEA with calixarin and in the presence of the quercetin. When using these three samples, a sign apoptosis is observed expressed in the presence of brightly glowing condensed chromatin in the image. Due to additional supramolecular interaction, the presence of lactic acid in the mixture with calixarin and NEA prevents the penetration of dox into the cell nucleus due to strong binding of the drug in the composition of nanoparticles. However, the increased cytotoxicity of this system clearly indicates the intercellular localization of nanoparticles, which can be realized to a great extent in mitochondria and to less extent in the plasma membranes, microsomes, and cytoplasm. So I hope I convinced you that macrocycles such as calixarin are interesting amphiphilic molecules because they can be modified with chemical groups that can achieve relatively low toxicity and ability to aggregate with polymers. The latter property is of particular interest since this aggregation is spontaneously process of creation of functional nanoparticles implemented in water without the use of organic solvents, application of temperature, and ultrasonic influence. Moreover, this supramolecular approach doesn't require large amounts of energy, which meets the criteria of the green chemistry. Obtained nanoparticles can increase the water solubility of hydrophobic antioxidants, which allows increasing their biocompatibility. And with excess of RNA relative to microcycles, the nanoparticles are capable of binding not only the lipophilic substance, but the hydrophilic drug. Despite the fact these water-soluble forms also demonstrated the cytotoxic activity against normal cells, can be said they use the oppositely charged polymer and microcycles led to joint aggregation, initiating the formation of promising nanoparticles for delivery of both chemotherapeutic agent and accident. I would like to thank person who took part in this work, Russian Science Foundation for financial support, organizing committee for giving opportunity to present our results in this night conference, and you for your attention. Thank you.